Welcome to the Explainer. Today, we're jumping into a really fundamental algorithm that honestly is a must-know for anyone getting started in natural language processing, logistic regression. So here's what we're going to cover in this Explainer. We'll kick things off with its core mechanism, then get into the super important step of turning text into numbers. After that, we'll look at how the model actually learns, how we can handle more than just two choices, and how we can tell if it's actually doing a good job. And finally, we'll talk about why this classic model is still a major player today. All right, let's get right into it. So at its heart, logistic regression is a classifier. What's its main job? Well, it's basically to find a line, a boundary that cleanly separates your data into different piles. You can think of it like an automated sorter for your email, trying to figure out what goes in the spam pile and what goes in the not spam pile. Now, you'll hear this term discriminative classifier, and here's what it actually means. It's laser focused on one thing. Discriminating, or just telling the difference between the groups. It doesn't waste any time trying to understand the deep story of how a spam email came to be. Nope. It just cares about finding the signals, the features that do the best job of separating it from a real email. So how does it actually do that? How does it go from looking at a bunch of words to making a confident yes or no call? Well, the model first calculates a raw score based on all the text. But that score could be any number, right? So to make it useful, it uses this really elegant little tool called the Sigmoid Function. Okay, don't let the mouth scare you. This is actually pretty cool. That W times X plus B part, just think of that as the raw score the model calculates. It could be a huge positive number, a huge negative number, anything. What the Sigmoid function does is it takes that number, whatever it is, and perfectly squishes it into a value that's always between 0 and 1. And that's fantastic, because now we can treat that number like a probability. And that leads us to the super simple decision point. If that final probability it calculates is 0.5 or more, the model says, yep, that's the one. It predicts the positive class, like spam. If it's anything less than 0.5, it predicts the negative class, not spam. That 50% mark is the decision line in the sand. Okay, so we've got the decision-making part down, but wait a minute. How does the model even understand the text in the first place? A machine can't read, "This movie was great." It needs numbers. And this right here is probably the most critical part of the whole process for NLP. We have to turn our words into numerical vectors. This is called feature engineering. You've got a few classic ways to do this. Bag of words, super simple. It literally just counts how often each word appears and ignores everything else. TF-IDF is a bit more clever. It boosts the importance of words that are really unique to one document, because those tend to carry more weight. And then you have n-grams, which are great for catching context by grouping words together. That way, the model learns that not good is the total opposite of just good. All right, so we can turn text into numbers, but how does the model actually learn which numbers and which words are important? Well, it's all about trial and error, really. The model's whole goal is to just make fewer mistakes over time. And to know if it's making mistakes, it uses something called a cost function. In this case, it's called Cross-Entropy Loss. And here's the genius part. It's like a really tough teacher. If the model is wrong but wasn't very sure, the penalty is small. But if it shouts, "I'm 99% sure this is spam," and it's dead wrong, oh boy, the penalty is huge. It basically forces the model to learn from its most embarrassing mistakes. And the way it learns is through this process called gradient descent. The best analogy is a hiker lost on a mountain in a thick fog, trying to get to the lowest point. They can't see anything, so what do? They feel the ground, find which way is downhill, take a small step, and then repeat the process. That's exactly what gradient descent does, taking thousands of tiny steps to find the set of weights that gives it the absolute smallest error. Now, a big danger, especially in NLP where you have thousands of words as features, is that the model can start to just memorize the training data. It learns all the little quirks and noise instead of the real pattern. We call this overfitting. The fix is something called regularization. It's basically an extra penalty we add that keeps the model simple, preventing it from getting too complex and helping it generalize better to new data it's never seen before. Okay, so spam or not spam is pretty straightforward, but what about the real world? A lot of problems aren't just a simple yes or no. What if you're analyzing sentiment and you need to classify a review as positive, negative, or neutral? Well, our standard logistic regression needs a little upgrade for that. And there are two main ways to do it. The first one, the softmax function, is pretty elegant. You can think of it like Sigmoid's bigger sibling. It runs a big competition between all the classes and spits out a probability for each one, and they all neatly add up to 100%. The other method is called one versus rest. It's more of a team effort. You train one classifier for positive versus everything else, another for negative versus everything else, and so on. Then you just let them all make a prediction and you go with whichever one is the most confident. So, we've trained our model. How do we actually know if it's any good? Well, you might be tempted to just look at overall accuracy, but in NLP, that can be super misleading. Imagine you're building a system to detect hate speech, where 99% of comments are fine. A model that just says everything's fine would be 99% accurate, but totally useless, right? We need better metrics. And this is where precision and recall are essential. Precision asks, of all the emails I flagged as spam, how many were actually spam? You want this to be high so you're not bothering people. Recall, on the other hand, asks, of all the real spam that came in, how many did my filter actually catch? You want this to be high too so your filter works. And the F1 score? That's just a nice way to combine both into a single number that gives you a balanced view. And if you really want to see what's going on under the hood, you need a confusion matrix. This little table is amazing. It shows you exactly where the model is getting things right, the true positives and true negatives, and more importantly, where it's getting things wrong. You can see the two different kinds of errors it's making, which tells you a ton about the trade-offs your model has decided on. Okay, I know what you might be thinking. We live in a world with these giant, powerful, deep learning models like BER and GPT. So why are we even talking about this old-school algorithm? Well, the answer is a huge, resounding yes. It still matters, and for some really good reasons. First off, it's the perfect baseline. It's fast, it's efficient, and it doesn't need a ton of data or computing power. But honestly, its real superpower, the thing that makes it so valuable, is explainability. It's not a black box. You can literally peek inside and see that the word free or congratulations was given a heavy weight for predicting spam. You can understand why it made the choice it did. And this really gets at a core principle in all of machine learning. You always start simple. Build the simplest thing that could possibly work first. You would be absolutely shocked how often a well-built logistic regression model is all you really need, and it can save you so much time and money. So the next time you're looking at a text classification problem, don't immediately reach for the biggest, most complex model you can find. Remember the power, the speed, and especially the clarity you get from starting with logistic regression. It's not just a beginner's tool. It's a powerful, interpretable, and incredibly effective model in its own right.